Good morning, everyone. I would like to present an overview of our journal titled Performance of Rocket Data Communication System using Wire Isolator on Sounding Rocket RX. My name is Kandi Rahardiyanti. And beside myself, our team comprises Shandi, Prio, Laksono, Khaula, Nurul, Hakim, Yuniarto, Wimbo, Nugroho, Andreas, Prasetya, Salman, and Kurdianto. This research is brought to you by the National Research and Innovation Agency, or Prio. Our presentation will be divided into several key sections. The first is introduction. We will provide an overview of the current state of rocket data communication system and the challenge faced in this domain. And the second is method. Here we will delve into the methodology we employed in our research and implementation of Wire Isolator in the communication system of sounding rocket RX. The third is result and discussion. In this section, we will present our findings supported by data and analysis to demonstrate the improvement achieved through our approach. We will also engage in a discussion about the implication of our result for future research and application. And the last is conclusion. Finally, we will summarize the key takeaways from our research and discuss potential direction for future work in this field. The first section is introduction. So the reason for conducting this research is because the RX ballistic rocket developed by the National Research and Innovation Agency, or PRIN, incorporates a data communication system for ensuring flight safety and stability. The system includes a microcontroller, a 6-job IMU sensor, a radio transceiver, switching cable, and a power supply. It monitors critical flight data such as temperature, speed, and altitude to optimize rocket performance. The MEMS accelerometer, known for its compact size and high accuracy, converts object acceleration into electrical signal. MEMS accelerometers are widely used across industry and are classified into piezoresistive, capacitive, and piezoelectric types. The RX rocket has encountered failure during flight tests, including data communication issue with the ground control station. Flight tests exposed the rocket to dynamic load and shock, resulting in vibration across a wide frequency range, especially during launch. To ensure stability and reliable control, the rocket designed for atmospheric research with high aspect ratio requires effective damping system. Improvement in thrust to weight and length to diameter ratio enhance range, but also increase vibration and shock. Optimizing mass distribution can improve directional stability. Vibration management is essential to protect equipment from fatigue, noise, and wear, which is critical for sensitive devices used in aerospace, military, and transportation applications. From various studies on vibration isolation system, Mosa et al. State that essentially vibration isolation systems are devices designed to minimize vibration. This technology aims to reduce the propagation and transmission of energy, creating a safer and more comfortable environment. While Hussein et al. Mentioned that vibration isolators are widely used to protect sensitive machinery such as electronic devices and military equipment from destructive shock and vibration. In the past several years, various equipment has been designed to protect structure from unwanted vibration and to reduce those vibration. Ledesma Ramirez et al. Indicate for the purpose of isolating vibration and shock, flexible support and/or effective mass increase of the system are commonly employed to lower the natural frequency of the isolated system. And Usula et al. Highlighted that wire rope isolators are frequently used to eliminate a vibration from various sources, such as flight system, sensitive electronic, and building structure. For the studies, to protect further studies show that a wire rope isolator control vibration and shock effectively in aerospace and mechanical engineering by leveraging their geometric and mechanical properties. So wire rope isolator provides flexibility in all directions due to the friction and sliding between the intertwined wires. As a result, they function as friction-type damper, utilizing stranded wire as the elastic component and column damping between the individual wire strand. Helical wire rope isolators are used for heavy equipment application, while polycal wire rope isolators are mainly used for mechanical and microelectronic application. As the length of the supporting wire increases and the natural frequency decreases, high mode vibrations are more likely to occur. So the objective of this research is experimentally analyze the damping capabilities of the wire rope isolator in the RX ballistic rocket to reduce the vibration and shock that occur during flight tests, ensuring that the data communication system can transmit the necessary data to ground control station for analyzing the flight characteristic of the rocket. The research also aims to assess the effectiveness of the four wire rope isolator installed in the RX rocket large and heavy data communication compartment between 30 kg in damping vibration and shock during launch. Success in obtaining the rocket acceleration data during the initial launch phase would lead to flight tests with a larger and longer rocket equipped with the wire rope isolator as vibration and shock damper. The method applied in this research involved creating a data communication system equipped with wire rope isolator damper, enabling the system to withstand vibration up to 8G and 15G. Before conducting flight tests, vibration tests were carried out to ensure that the data communication system equipped with wire rope isolator vibration damper could accurately record acceleration data and that the system itself will function effectively under vibration condition. And this picture illustrates the process flow for the testing performance of data communication system. The picture on the left illustrates the data communication system equipped with wire rope isolator. The rocket data communication system consisting of a 6 inertial measurement unit with accelerometer and gyroscope sensor is based on both the object and navigation coordinates. The IMU used in this research is the MPU 6150, consists of accelerometer and gyroscope, and AVXL 78 accelerometer. Both are capable of measuring acceleration between 4G and 50G. For the data communication system to function and transmit acceleration and trajectory data to ground control station, a power system is required. The power input to the system is DC with a voltage of 7 volts, powering a 5-volt serial data circuit and 3-volt sensor circuit. The output from the system transmitted via 5-volt radio transmitter, which operates at frequency of 900 MHz and can communicate up to 100 km with a data rate of 345 kilobit per second. The rocket data communication system weight is 30 kg. The rocket experienced vibration during its launch, which will impact the data communication system. To minimize this vibration, damper are required and installed in the rocket data communication system. Based on the install position and the direction of the load axis acting on the damper, there are 4 types of mounting orientation. The top picture is illustrate the compression wire rope isolator mounting axis. The second picture shows the 45-degree compression or roll position of the wire rope isolator mounting. The third picture shows the fixture of the wire rope isolator mounting position, while the last picture depicts the fixed roll of the wire rope isolator. In this study, we use 4 wire rope isolators, stainless steel damper installed in the rocket data communication system compartment with type of perpendicular loading or compression. You can see the picture on the left. And the dimension of wire rope isolator we use are shown in the picture on the right. For the vibration test, the placement of RX rocket data communication system that has been installed with wire rope isolator and equipped with a tube on the vibration test machine can be seen in the picture on the left, and on the right is the picture of basic component of electrodynamic vibration testing system that consists of 5 components. And this is the 5 component of electrodynamic vibration testing system. The first component is control computer. This is the main control unit that provides signal and commands to the other component in the vibration testing system. The second component is vibration controller. This is the signal generator that produces the desired vibration signal to drive the electrodynamic shaker. The third component is amplifier. This component responsible for amplifying the signal generated by the vibration controller to the appropriate level required by the electrodynamic shaker. The fourth component is electrodynamic shaker. This is the primary component that generates the vibration, which are then applied to the test object. And the last one is accelerometer. This is the measurement device that provides feedback signal to the control computer regarding the actual vibration experienced by the test object. To design a large, high-performance sounding rocket, key considerations include achieving high acceleration, providing substantial initial thrust, and incorporate effective vibration and shock damping system. And this study investigates the integration of 4 wire rope isolator within the RX rocket data communication compartment, arranged in compressive configuration and aligned to optimize vibration attenuation. This setup aims to mitigate vibration encountered during both ground-based vibration tests and in-flight tests. While earlier studies have explored wire rope isolator system, they have not explicitly addressed its influence on data communication system on sounding rocket. The method proposed in this research utilizes wire rope isolator dimension, as shown in a picture before this, resulting in a wire rope isolator stiffness value consistent with calculated result. Specifically, the wire rope isolator stiffness is lower than the calculated maximum allowable stiffness. And this is the calculation. The characteristic of the damper consider static load in W, deflection in D, and shock stiffness in KS. And with a load mass of 30 kg, the total supported load data is obtained as follows: 294.3 Newton. And the number of wire rope isolator we use is 4 units. So the static load per isolator is 23.58 Newton. The rocket propulsion operates by generating an excitation frequency of Fi, 93.3 Hz. The system response natural frequency for 80% isolation is 31.1 Hz. The maximum isolator vibration stiffness is 286 kN per meter. After calculating the load per damper and the maximum damper stiffness, both parameters are compared with the maximum static load that the damper can support and actual damper stiffness under the condition. First, calculated W lower than maximum damper static load, which is 73.58 Newton, lower than 80 Newton. And the second condition is wire rope isolator stiffness lower than calculated maximum stiffness, which is 125 kN per meter, lower than 289 kN per meter. So the next section is result and discussion. From the vibration test, the test was performed by gradually increasing and decreasing the frequency to observe dynamic acceleration data. The frequency range used started from 0 Hz up to 2 kHz. The vibration test result recorded by the frequency measurement system installed on the vibration machine. Vibration testing was performed under 2 conditions. The first is constant sweep vibration, and the second one is random vibration. The result of the constant sweep vibration test on the vibration machine conducted at frequency ranging from 4 Hz to 600 Hz The test started with an excitation of 1G and went up to maximum 8G. The graph on the left shows no difference between the excitation input and the control accelerometer reading. And from the second vibration test is random vibration test result at high frequency vibration level obtained was 0.4 G square per hertz, while excitation of 0.03 G square per hertz, while at frequency 900 hertz and 1 G square per hertz, while excitation of 0.04 G square per hertz at frequency of 1600 hertz. The power system for the data communication system was turned on, and the start of vibration testing to record acceleration data from sensor installed in RX rocket data communication system. And during the constant sweep vibration test, the recorded acceleration value were 8.37 G in picture A and 8 G in picture B. In the random vibration test, the acceleration value were 20.37 G, so in picture C, and 8 G, shown in picture D. The consistent recording of acceleration data by the sensor in rocket data communication system during vibration test is attributed to the wire rope isolator installed in the data communication compartment, which effectively dampened vibration and shock within the frequency range of 0 Hz to 1500 Hz. The higher G reading on the test object sensor compared to the vibration machine reading are usually caused by phenomena such as resonance, difference in dynamic response, nonlinear behavior, sensor placement location, and the swing effect when the vibration machine oscillates. This is the natural mechanical response to external vibration during testing. However, despite the higher G value received by the communication system IMU compared to the vibration machine maximum, the communication system continued to function correctly and transmit a signal without interruption or system shutdown, indicating that the wire rope isolator damping system performed adequately. Based on the RX rocket flight test data received on ground control station, the performance of the stainless steel wire rope isolator installed in the rocket data communication system can be analyzed. So from the picture above, show that the acceleration data obtained during flight test, which reached 8G and 9.3G. Based on the vibration test result, the acceleration value of 8G to 12G occur at frequency between 800 Hz and 1500 Hz. This correlation between acceleration and frequency in the vibration test and the rocket flight test demonstrate that the wire rope isolator installed in the data communication compartment were able to dampen vibration and shock experience during a rocket launch from the pad. The last section is conclusion. From this study, use 4 stainless steel wire rope isolator damper with perpendicular or compression loading to minimize vibration experienced by the 30 kg rocket data communication system during launch. The wire rope isolator damper with a rigidity of 289 kN per meter and total static load of 294.3 Newton were able to withstand acceleration up to 9.37 G during flight test and 12 G during vibration test, ensuring stable data transmission to the ground control station during the rocket flight. Although the mounting orientation and the number of dampers meet the requirement, there are other external variables that arise, such as swing effect. The swing effect causes a shift in the acceleration value of the rocket data communication with vibration decrease acceleration of plus minus 1G. For future works, explore alternative damper configuration to further improve performance in complex flight conditions. The swing effect will be a reference factor for the selection of the position of the ballistic rocket damper in the next study. There are several positions that can apply to the placement of the wire rope isolator position. namely the position of the reducer 45-degree compression or roll, fixed shear, and fixed roll. And this is the list of reference that we use in our research. This is the end of our presentation. Thank you.